Okay, good morning. So we continue our lesson in complex numbers. So today we talk about what we call the complex plane. So as you have learned so far, the complex numbers are a little bit abstract, so we have to imagine them abstractly, and then probably based on evolution or something, we are more comfortable with figures and shapes. So that is an idea to somehow give us a way to imagine complex numbers as shapes or geometrical objects. So that we have the notion of the complex plane, and actually it is nothing very new. So the only thing is that you have your coordinate system as before, but instead of calling the x-axis, the horizontal axis, to be the x-axis, you call it the real axis. And instead of calling the vertical axis the y-axis, you call it the imaginary axis. And then, as before, this is the origin, and of course these two are perpendicular. So these two axes construct what we call the complex plane. And now, from now on, every complex number, which is an abstract notion in our head, can be viewed as a point on the complex plane. Yes, that's a way of representing geometrically a complex plane. There are two representations for a complex. There are two representations for a complex number. One of them is representing them as a point. The other one, which will be the topic of the next lesson, is representing them as a vector. Okay, but for the time being, let us just concentrate on this. If I give you the complex plane, the complex number z to be a plus bi, so you go on the real axis, depending on the sign and the value of a, you choose a point on the real axis, a unix, yes? So for example, assume that in this case a is positive, and this is a, and then you go and choose b on the imaginary axis, wherever it is, and then as before, so what you do, you just make this point, and then you say that this point represents this complex plane. That's it. So instead of having the x-coordinate, you have the real part. Instead of having the y-coordinate, you have the imaginary. Yes, so that is what. So from now on, we can imagine a complex number as a point on the complex plane. Okay. So for example, if I ask you represent point 1 minus 2i, then what you're supposed to do, so you have this, the real axis, the imaginary axis. The real part is 1, the imaginary part is negative 2, and then you get this one. So this point is your z. I don't know, for example, if I say w is negative 2, so what you do, you go 2 units to the left, the real part is minus 2, the imaginary part is actually 0, yes? So this means that this is double. So every complex number can be viewed as a point on the complex plane. That's a very simple idea, yes? Any questions? Yes?
Do you ever write out the imaginary part and the real part as like a coordinate? In the same way as we write coordinates?
To be honest, the abstract way, if you go to higher mathematics, they don't define complex numbers like this. They define complex numbers as what you mentioned from the beginning. Yes, and then they give definition to what we mean by I. So they define I to be this ordered pair. Okay, but that would be a little bit. Of course, the consequences and everything would be the same, but it would be on a firmer, rigorous mathematical way of doing things, yes? Okay, so, do you have any questions regarding this representation? So, one question, for example, can you tell me how z and z bar are related on the complex plane? Do you remember what was z bar? So if I give you z, a plus bi, and then z bar will be a minus bi. Yes? So how they are related on the complex plane? They have the same real parts, but the imaginary part is opposite. Yes? So what will happen for these points? If z is here, z bar would be the mirror image of that with respect to the real axis. Yes? So z and z bar are related like that. Okay, so let me ask you another question. How do you think these two are related? Z, I give you a point z, whatever it is. This is one point. I take this z and multiply it by I. This becomes another complex number. Yes. So I give you a complex number, whatever it is. It's somewhere on this plane. Then I will take that number, multiply it by I. It becomes a new complex plane, a new complex number. So if it's a complex number, it will be somewhere on the complex plane. Can you tell me how these are related? You need to think a little bit about it. So is that understandable? For example, if I give you z equals to 2 plus 3i, it's one complex number. I multiply it by I, it becomes 2i plus 3i squared. But 3i squared becomes negative 3 plus 2i. So it is not, you cannot say that it is the mirror image or whatever, you see, because 2 was here, now it is here. It was 3 that was here, now it is minus 3 that's here. So you need to see what is happening if I multiply a complex number by I. So for example, if I want to draw this one to understand, so you see here I have the real axis, I have the imaginary axis, and then I have 2 and 3. Yes. So this is my z. But now if I go to iz, it is minus 3, minus 1, minus 2, minus 3, and then 2i. So it's here is iz. So what's happening, do you think? So it is not the mirror image with respect to the imaginary. The mirror image will be here. I don't know. So can you feel what's happening? Yeah, that's correct. So what's that? It's rotation, yes, exactly. So what's happening is that what rotation with respect to which center and which angle? 90 degrees, exactly, with respect to the origin. So if you take this point and that point, the length here, how much is the length here? I hope that you agree with me from the length point of view, this is exactly the same length. Do you agree? Yes. Why? Because Pythagoras Theorem, this is 2 units and this is 3 units. So if I ask you what is this length, you would say that square root of 2 squared plus 3 squared, whatever it is. And if I ask you what is this length, now this one is 3, this one is how much? 2, and that would be the same thing. So the length here and the length there are the same. Yes? And then the point is that if the lengths are the same, so it is clear that if I put the needle of the compass here and open it like this, when I do this circle, it will definitely pass through this point. That is clear, so it's a rotation. But how much is that rotation? You need to measure this angle. Okay, so intuitively you might say, so what's this angle? So this, if this angle is alpha, yes, this angle is how much? Alpha again, yes? And this angle becomes beta, yes? So alpha plus beta is 90. So this alpha plus this beta will also be 90, so the leftover will also be 90. So that's rotation by 90 degrees. That's a good thing. Of course, in our course, in this lesson, we will not talk about these kinds of transformations, but that is understandable. So if you multiply a complex number just by I, it seems that it is equivalent to rotating the point about the origin counterclockwise by 90 degrees. Yes? Is that understandable? So that's just an example to understand the complex plane a little bit better. Okay, so these kind of questions that I want to mention here is important for this complex plane. So let me write as an example. So this is important, okay? So they ask you these type of questions. In each case, specify all points Z on the complex plane with a given property. So for example, I give you this, imaginary of Z equals to 1. So in each case, specify all points Z on the complex plane with a given property. So I am looking for all complex numbers Z on the complex plane so that the imaginary part of those numbers is 1. So what is that? If you want to specify it, yes?
Infinite amount of numbers.
Yes, but where? So you have to specify it exactly. Of course, there are infinitely many numbers, yes?
At the point 1, the imaginary
Yes?
component 1.
Yeah.
And then all real
Horizontal line.
horizontal line.
Yes, exactly. So that's exactly what you're saying. So this means that if I go this to the complex plane, this is the real axis and this is the imaginary axis. I am interested at a point, at all points, I'm interested in all points so that the imaginary part of Z is 1. For example, is this one of the acceptable points if this is 1 unit? Yes, because the imaginary part of this number is 1. I don't know if this is acceptable. No, because the imaginary part of this is larger than 1. So where are the points that are acceptable? Of course, all the points that lie here, yes? So, and then you want to represent it, so you just draw a solid line. That's it. And of course, it will continue forever from both sides. So if I ask you draw a graph for this horizontal line will be the graph of this equation, yes? And this is just 1 unit. Okay, so the idea is this, but it might be a little bit more complicated. So for example, another simple one is this. The real part of Z should be less than or equal to 3, strictly larger than 1. So I am interested in all complex numbers on the complex plane for which the real part lies somewhere between 1 and 3, excluding 1, including 3. Yes? So what is that? So let us draw a complex plane here for the time being. So that's complex plane, real part, imaginary axis. Okay, so what is that? Can you describe it in words? Yes?
A vertical line or two between the point 3 of the real numbers and not including 1, just dotted.
Okay, so that's exactly what you said. So the real part of that number should be somewhere between 1 and 3. For example, this point is not acceptable because the real part is negative. I want to have the real part exactly between 1 and 3. So exactly as you said, this is 1. This is 3, for example. And then this should be dotted line. Oops, okay. This should be a dotted line. What that exactly you have to do with dotted line? It means that I am showing that I am excluding 1. Yes? But on 3, it should be a solid line. Yes? But is that it? Or I should, everything in between. So you need to convince people that you know about it, yes? Or at least you need to know yourself. So that is what you see. This is excluded, this is included, and everything between is also included. So this strip is actually a representation of this inequality, double inequality. Is that understandable? Okay, now let me give you another one. And I want to wait for you. It's more tricky. So these are simple ones in your book. Okay? Okay. So number 3. Let me write this equation for you. 2z plus 3z bar is equal to 6. No, it's equal to 5 in my writing. And then let me write one more. 4. This is more tricky probably. 3 times z bar plus imaginary part of z. And then plus 3z greater than or equal to 1 minus real part of z minus 2. No, there is also a 2 here, sorry. For the time being, don't worry about this complicated one. Consider about this one. And then when you get some lessons from here, we can use the same idea, but of course harder here. So I give you a little bit of time to think about it. Okay, could you solve the first one? Any idea of how we can do the first one? Or at least can you tell me how many points you expect? So if I ask you how many points you expect here, you say infinitely many. How many points you have here? Of course, infinitely many. How many points do you think you will have here? Is it 1 point or more? Yes?
My initial thought was 1.
Yeah, I think it should be 1. Yes? Okay. But how can you find that point? So in principle, this is not something new. I put it under this discussion, but you already know what to do with this one. That's an equation. Yes? So in principle, you need to find your z. But how can I find my z from such an equation? I told you that trick, yes? So how should I do that? And by the way, what I am telling you right now in this case can also be used for all possible cases. And I really recommend you to learn that, because if that's complicated, I cannot myself guess it at all. So I have to do some calculations to understand what is the shape. Yes?
Z bar is just minus z.
No. Z bar, the imaginary part of z is minus the imaginary part of z, not the total. Yes. So in these kinds of questions, in which z and z bar, or z bar, some part of something is also included, the first thing that you need to do, you would say that remember this trick, it's simple, and it's very natural, by the way, x plus yi. And then, if this is the case, you have to put it back into this equation. Yes? So if you put it in this equation, so then what happens for z bar? Z bar becomes x minus yi. And then you have these two, you put it in this equation. This becomes x plus yi plus 3 times x minus yi is equal to 5. And then you try to solve this, make it simple. So 2x from here, 3x from here is 5x. And then you have 2yi minus 3yi, which is minus 1yi is equal to 5. So your intuition was actually correct. So what is the conclusion now? The left-hand side is a complex number. The right-hand side is also a complex number, yes? So this means that I have two real complex numbers equal, but this can happen if and only if the real parts are the same and the imaginary parts are also the same. Yes? So this means that x is just 1, there is only one value for x, and there is only one value for y. Yes? So then it means that what is z? Z is just 1 plus 0i. Yes. And then if you want to represent it as you were able to guess at least correctly, it's just one single point. And that single point is 1 here. So the representation of this one is just one single point. Yes, is that clear? Now that you have refreshed your memory, I can give you 5 minutes to find this. Draw a graph or a picture represents this inequality. Okay? That's the same idea, more involved algebraically. Any questions, by the way, here? Okay, did you come close to some idea?
Yeah.
Yes?
No, they didn't.
Okay, so what I'm supposed to do?
The same thing.
The same thing, but I need to do some calculations. For example, so if you want to solve this in the exam, so you would say that let z be equal to x plus yi. Then I have to calculate some parts, yes? So here, what I need for this inequality, I need z bar, okay, so I do it. So z bar is x minus yi. I need imaginary part of z. So imaginary part of z is what? Is y. That's good. Okay, I need z minus 2 first. So z minus 2 becomes x plus yi minus 2. But these are real, so I can combine them. And then it becomes plus yi. Then if I ask you what is the real part of z minus 2, you can answer it is x minus 2. Okay, so I think these are the only ones that I need, so I put everything here in this inequality. So this becomes 3. Instead of z bar, I put x minus yi. And instead of imaginary part of z, I put y. And then plus 3 times the z itself. Yes. And then greater than or equal to what? 1 minus 2 times the real part of that. Yes? So it turns out to be an inequality. But by the way, this is very strange. I will talk about that later. So that is very good that I didn't write something randomly, because then we will be in trouble. I will talk about that later. So then I multiply this in, so this becomes 3x minus 3yi plus 3y, and then it becomes 3x plus 3iy is greater than or equal to 1 minus 2x plus 4. And then, fortunately, this part is cancelled, otherwise I would be in trouble. Yes, I hope that you feel why. I will talk about that later. The 3x plus 3x is 6x plus 3y greater than or equal to 5 minus 2x. Yes? And then what happens, for example, I can move it to the other side. It becomes 8x plus 3y is greater than or equal to 5. Yes? At least, if I haven't done something wrong, how many of you got this inequality? Yeah, good. So at least the chance of making mistakes is now very low. Okay, but now how can I draw this? If I tell you draw equality, in principle you shouldn't have problems with that, yes? If instead of inequality I ask you to draw a picture or a shape that is represented by this one, that is in principle a Math 1C problem, yes? That is what? It's a line, yes? For example, if you want to find the slope, you move 8x to the right-hand side, make y alone by dividing by 3. So this is the k value, this is the m value. So this is actually a line. So let me just try to draw this line by giving nice numbers. So for example, do you have a good number? So for example, let me give x to be 0, and then y becomes 5/3. Let me give y to be 0, x becomes 5/8. Yes? And then, for example, let us exaggerate the picture a little bit. So if I go to the complex plane, so I find these points, 0, x is 0, y is a little bit more than 1. Yes, x is 0, y is a little bit more than 1. So let me try to assume that this is 5/3. Yes, that is one point. Another point is that you have 5/8 and y is 0. So 5/8 probably will be smaller than that, so something here. Assume that this is 5/8. And then I join these 2 points. Yes. This line that you see here, which goes forever from both sides, is just the equality part. Yes? Every point lying on this line makes this one equal to 5. But equality is one scenario. I want to include greater than 5. So how should I do that? It should be either on that side or on this side. So how do you decide? Sometimes it is tricky, so I don't recommend you just guess. So I would say that this line is equality, so either I should be on this side or I should be on the other side. So the trick is, I usually use this trick. I choose a point which I am confident about on which side it lies. For example, by this picture I realize that the origin is on this side. Origin has 0 and 0. I put 0, 0 here. 0 plus 0 greater than or equal to 5. This is false. Yes? So it means that I cannot go on the left-hand side, because if I go on the left-hand side, I will also include the origin, which gives something wrong. So it means that I go above. And then, by the way, that is a standard that, because instead of coloring things, you can just put this something like this arrow and showing that this is on this side. But in principle, if you want to color it out, so you have to color this half plane on the right hand side. Yes. So that is a representation of this inequality there. Yes. But let me just draw your attention once more. It would be really problematic if somehow I survives. Why is that? So assume that I did the calculation, so when I was designing the question, I fine-tuned the numbers in a way that I can get rid of I. If I couldn't get rid of I, what was my problem then? For example, so let us assume that I will get 3x and then plus iy greater than or equal to 2. Then what was my problem? Yes?
Then you write 2 as an imaginary number, and you take x and y to be equal to the real and imaginary components of that side.
Okay, can you tell me exactly what to do? This is inequality.
Of course, this is not for the inequality, this is for the equality.
Exactly.
But
the notion of inequality is much harder when it comes to complex numbers. And why is that? Why do you think the notion of inequality is harder in complex plane? Or actually doesn't exist at all, unless you want to define it in some way. Why is that? Because if I give you two complex numbers, which one is bigger? We haven't defined that yet. Yes? For example, if I tell you z is equal to 1 plus I, and I tell you z is, I don't know, 2 plus 4i, which one is bigger? I want you to understand, we haven't defined the notion of order for complex numbers yet. So that we don't know which one is bigger. Is that understandable? We cannot say that because it contains bigger numbers, it is bigger than that one. Yes? So what about this one then? If I keep this one 1 and I make it this one. Or, let us make the scenario worse. I make this one bigger and make this one smaller. Okay, this one is bigger than that one, or the other way around, or which way? So I want you to understand, we have to, if we want to say something about the order between complex numbers, I have to be more precise. Yes? Because I can increase the real part, in the same time I can decrease the imaginary part. Now I'm asking you, do you think the number will grow or will decrease? You know, I just want you to see it's not that trivial. Is that clear? So we haven't defined the notion of order, and probably you will not see it if you don't go to pure mathematics, yes? But I will talk a little bit about that later. Okay? So can you give me a feeling, for example, which one do you prefer to be bigger? Do you have any idea? Using the notion of complex plane, so realize that every point, every complex number is a point in the complex plane. What do you think would be natural in the beginning to define as the order? Yes?
That the further right and up the point is the bigger.
Up, okay. So for example, so which one is bigger in your system of ordering?
The second one is bigger than the first.
So what?
The second one is bigger.
The second one is 1 plus 4i. I'm sorry. The second one is 1 plus 4i. So this is 4 and 1. This is 1 plus 4i. Okay, the other one is, for example, 1 plus I. So 1 plus I is somewhere here. And then you have another point, 3 minus I, which is here. This is 3 minus I. This is 1 plus I. So you have these 3 points. So you are considering this bigger than all of it?
No, the further up and right.
Okay, but so how can I compare? So these, you are saying that between these two, this one is the larger.
Yep.
And between these two, this one is the larger. Between these two, this one is the larger. So in principle, you are saying that one.
No, I'm prioritizing up.
Okay, so tell me, so I want to order them. Assume that I want to arrange them in ascending order. Which one comes first?
1 plus 4i.
1 plus 4i is the largest one.
Yes.
Okay, is greater than?
1 plus i.
1 plus i is greater than?
3 plus i.
3 minus i. Yes?
That's just how it feels, how it seems.
Yeah, might be. But I just want to understand that this might work or not. But because might be the feeling, the distance to the origin is also something natural. So why the distance to the origin cannot be a good measure of ordering complex numbers?
Because it doesn't take negatives into consideration.
No, it contains. So I mean, so for example, can I say that this is larger than this one because its distance to the origin is greater than the distance from the origin of that one? So I would say that I measure the distance from a natural number to its origin, to the origin, And if it is a smaller, I would say this number is smaller than the other one. Why do you think this will not a good idea, even though it seems natural in the beginning? So because you know that the notion of order is so implemented in our brain, we don't even think about it. But if I give you a bunch of abstract objects, it is not necessary that we can order them in ascending order, or we have to define an order for them. So why do you think it's not a good idea? Because then, if I take a circle about the origin, then I consider this point and this point, then which one is larger? The distance from this point to this and the distance from this one to this would be the same. So then we cannot compare these 2 points, which one is bigger than the other one. So if we consider the distance to the origin, as the measure of the order, we will have this problem. Then we cannot compare these points, because the distance from these points to the origin are the same, the distances, yes? So we come back to this one. So I just want to mention that if I was not eliminated by fine-tuning those numbers, then I will have problems, because we haven't defined the order, what is the meaning of a number being bigger than the other number. Okay, now let us continue to the next part of the lesson, which is also very important, and that is called the absolute value or the modulus of the complex number. I will come back to the notion of order in a while. So here, so the absolute value or modulus of a complex number and that is a very, very simple thing. So the complex number, assume that you have a complex number z. The real part is A, the imaginary part is B, and then I want to talk about the absolute value. So that is denoted exactly as before. Then I define it to be square root of the real part to power 2 plus the imaginary part to power 2. So that is the definition. So in principle, I have to put a semicolon here. It means absolute value of z is defined to be equal to. This means is defined to be equal to this. That's very simple. And what is the geometrical interpretation of absolute value of a complex number? What is that? So if I have the real axis and the imaginary axis, and then here is A, here is B, and this is my point, absolute value of z is exactly the distance from z to the origin. Yes? So if I take this one from here to here is absolute value of z. So remember, the geometrical interpretation of absolute value is a distance. Distance from the point on the complex plane to the origin. For example, if I give you z equals to 1 over 2 plus square root of 3 over 2i, and I ask you to calculate the absolute value of z becomes equal to a square root of the real part squared plus the imaginary part squared. And then what happens? This becomes square root of, this 1 to power 2 is 1/4. This becomes 3/4. And then this becomes square root of 4 over 4, square root of 1, which is 1. So if I give you this complex number, and I ask you to calculate the absolute value, it becomes 1. What does it mean? It means that if you go and find this point on the complex plane and measure the distance from this point to the origin, it becomes 1 length unit. So what do you think about this one? if I give you z equals to I, and I ask you to calculate absolute value of z, then you would interpret z to be as what? 0 plus 1i. And then what you write is becomes square root of 0 to power 2 plus 1 to power 2, which becomes 0 plus 1, which becomes square root of 1, and that is 1 again. So the distance from the origin to this point is also 1. The distance from the origin to this point is also 1. So the absolute value of both of them are 1. So what do you expect for absolute value of minus 5? Because minus 5 is a real number. If I ask you what is the absolute value of minus 5 when we haven't talked about complex numbers, then immediately you will tell me 5. But now I told you that every real number can also be viewed as a complex number. The new formula should give me the same value, otherwise I will have inconsistencies, yes? So let us see if that's correct or not. What you need to do, you need to interpret minus 5 first. Of course, you really don't need to do, if I ask you what is the absolute value of minus 5, you can immediately answer 5. But I want to motivate you, there is no difference between these two definitions. So minus 5, when it comes to real numbers, can be interpreted as minus 5 plus 0i. And if I calculate absolute value of minus 5 using this formula, this will give me minus 5 squared plus 0 to power 2, which becomes square root of 25 plus 0, which becomes square root of 25, which becomes 5. So you see that for the real numbers, we really don't need to go through this long process. We just simply answer 5. But even if you use the formula, it will give you the same answer. Otherwise, we will be in trouble by that. Yes, we would have been in trouble. Okay, now let me just continue and write a theorem. This theorem is actually scattered in the problems in the book. I want to write them in one place. So if you want to go to higher mathematics, it is better to know them as theorems rather than problems. Because when we name something as a theorem, it means that it is important and it is useful for other parts of the problem. So, let me write theorem. I will go more through the proof of them, not because of the theorem, because they are in the book. You have to know how to calculate. So theorem, properties of the absolute value. Okay? So I would say that let Z and W be complex numbers. Then, okay, this one is very interesting, very simple, very important. If you multiply a complex number by its conjugate, it becomes absolute value squared. Yes? So if you multiply a complex number by its conjugate, it becomes absolute value of that complex number squared. So the second thing is that absolute value of z and absolute value of z bar are exactly the same numbers. So number 3, this is also important, so let me put a star here. Absolute value of z minus w is equal to the distance between z and w as points on the complex plane. Yeah, this is also important. You have to know this. So number 4, let me write number 4 here. Absolute value of z times w is equal to absolute value of the first one multiplied by the absolute value of the other one. And then the same thing happens for absolute value of the division. It becomes absolute value of the numerator divided by absolute value of the denominator. Of course, in that case, W shouldn't be equal to 0. Okay, so let me write and cross it over right now. That don't think that this will go further. Absolute value of W, Z plus W. If you write absolute value of the first one plus absolute value of the second one, or for the negative sign, please write it and cross it over. That's not correct. We will discuss about that. We will tell which one is correct. But for the product and division, it's correct. Okay, so here I want to actually start going through them one by one. And then after that, we want to give some important problems from the book actually that uses this idea. Okay. So the first one, I think, is more or less clear for you why. If I want to prove the first one, what should I do? I would say that, number one, I would say that let Z be equal to A plus BI, for example. Then Z bar becomes what? A minus BI. So therefore, what I have, Z times Z bar becomes equal to A plus BI multiplied by A minus BI. But this is the conjugate pattern, so it becomes the first one squared minus the second one squared. But this becomes A squared minus B squared I squared. But I squared is negative 1, so it becomes A squared plus B squared. But that's exactly what? It's exactly absolute value of Z squared. Yes, you see it on the board. No, I cleaned that. So what was the definition of absolute value? The absolute value was the square root of A squared plus B squared. So when I have this one, it is the square of that. Yeah, is that clear? Okay, so number two, first of all, tell me, could you expect that this is true? Absolute value of Z is equal to absolute value of Z bar based on geometrical picture. Yes?
I mean, just because it's the
Mirror image.
yeah, it feels natural.
Exactly. The distance will not change. So we just learned that if here is Z, then Z bar would be the mirror image here. But this transformation actually doesn't affect the distance. The distance remains the same. So from geometrical picture it is clear, but if you want to prove it algebraically, you would say that absolute value of Z is the square root of A squared plus B squared if Z is this one. But absolute value of Z bar would be A squared plus minus B squared because Z bar is this one. But this also becomes the same number. So this means that absolute value of Z is equal to absolute value of Z bar. Okay, but let us talk about this. That is important to know. Okay? So number three, what is the meaning of that? This means that if I have a complex plane, real part, imaginary part, if you give me two complex numbers Z and W, and if I go and find them on the plane, for example, one of them assume it to be here, another one to be there. If I ask you, what is the meaning of absolute value of Z minus W, it's very nice. It measures the distance from Z to W. So it means that this distance is exactly equal to the absolute value of Z minus W. Of course, it doesn't matter. You can write absolute value of W minus Z. So this picture, it's important to have in mind. If you have two complex numbers on the complex plane, if you somehow need to talk about the distance between these two, always remind yourself of this quantity, absolute value of Z minus W. But why this is true, it's very simple. Because if z, for example, z is a plus bi, w is c plus di. Then if I ask you what is z minus w, z minus w becomes a minus c plus b minus di. And now if I ask you what is the absolute value of z minus w, it becomes the square root of real part squared plus imaginary part squared. Yes, but I hope that you remember this formula from Math 2C. That is the distance formula. The difference between x coordinates squared, the difference between y coordinates squared. So that's exactly the distance between these two points because of the distance formula. Yeah, is that clear? Yes? Do you remember in Math 2C, if you had 2 points with coordinates x1 and y1, another point with coordinates x2 and y2, if you want to measure the distance between them, call it d. D is the square root of the difference between x coordinates squared plus the difference between y coordinates squared. Yes? You see, this is exactly this one. But instead of the x coordinates, I will have the real parts. Instead of the y coordinates, this time I have the imaginary parts. But that's exactly the same formula. Yes? So the idea is important. Remember this. Okay, let me ask you one question. Can you just tell me what is this one? How do you interpret this one now? This was the distance between z and w. It is crucial to have negative sign in between. Because you see that if I do not have negative sign in between, then it becomes positive, but the distance formula includes negative signs. So how do you interpret this one then? Can you interpret this also as a distance? If yes, the distance from where to where? What? The distance from where to where? So this one is positive. You don't want to have positive sign here. There is one way mathematically doing it. Write it as z, put it minus, and then put another minus. Yes? Z minus minus w. But whenever I have the negative sign in between, that's good. I can interpret it as a distance. But this becomes the distance from z, not to w, from z to minus w. So the distance from z to minus w. Or how can I interpret it alternatively? I can imagine it as w minus minus z. So then I can write or the distance from w to minus z. So this is also good to know. I recommend you to write some kind of remark for yourself that if I have the absolute value of the difference, you can immediately interpret it as the distance between those two numbers. But if you have positive between, you can interpret it in two different ways, yes? But hopefully understandable, yes? Okay, now let us go and try to prove one of these, and you can help me. This is one exercise, I think, in the book. Yeah, okay. So I will prove number 4 for you, and then you can prove number 5 for yourself. But the ideas are exactly the same. So you want to prove number 4. So what do you think I should do? I want to prove that absolute value of the product of two complex numbers is equal to the absolute value, the product of absolute values. It means that these two operations are commutative. I can interchange them. If I multiply first and then take absolute value, it becomes the same number if I take absolute value first and then multiply it. Yes? So the result will be the same. We want to show that this is not a coincidence, this is always true. So what should I do? I would say let, exactly as before. So I would say let z be equal to a plus bi, and z as w be equal to c plus di. Yes? This is one way. Okay, then z times w is equal to a plus bi multiplied by c plus di. Then it becomes ac. bi times di becomes minus bd as the real part. And then a times d I, b times ci, I factor an I out. So this is the product. And then if I ask you what is the absolute value, you will tell me the absolute value is the square root of this one squared plus that one squared. This is the definition of absolute value we learned just now. If I want to take the absolute value of a complex number, I have to raise the real part to power 2, the imaginary part to power 2, add them, take the square root. But then what can I do? I have to simplify it. So let me just use the squaring rule. The first one squared, the 2 times the first one times the second one, the second one squared. The same thing here. A squared, d squared, 2 times the first one times the second one squared. Agree? But the nice thing is that this one and that one are exactly the same. A, B, C, D minus 2, A, B, C, D positive 2. So they are cancelled. Yes? And then what happens? Between these two, I can factor a c squared out. Okay, so let me between these two. Let me take between these two. Doesn't matter, of course. I take a squared out. It becomes c squared plus d squared. And then between these two, I take a b squared out. It becomes d squared plus c squared. So between these two, I factored a squared out. Between these two, I factored the b squared out. But then c squared plus d squared appears here and there, so I can pull it out again. So this becomes the square root of c squared plus d squared multiplied by a squared plus b squared. Yes. And then I can decompose this as to square root of a squared plus b squared multiplied by square root of c squared plus d squared. This will work. But then if I ask you what is this one, this is exactly absolute value of z. And what is this one? That is absolute value of w. So I was able to show that absolute value of z times w is equal to absolute value of z times absolute value of w. But there was an easier way to do it if you use number 1. Yes? So let me also do that one. That's also good experience if you have it. So if I want to prove it in a different way, I would say that absolute value of z times w squared, for the time being, is equal to this number multiplied by its conjugate. Yes? Why this is true? Because of the first item. If I have a complex number, absolute value squared, I can write it as that number multiplied by its conjugate. So what I have done here. But do you remember I told you in the previous session that if you have the product and if you are interested to take the conjugate, you can do it like this. You can take the conjugate for the first one, you can take the conjugate for the second one. Do you remember that was one thing we proved? But now what can I do? I can take these two and put them together, and take these two and put them together. But now according to the first item again, z times z bar is absolute value of z squared, and for the same reason this becomes absolute value of w squared. And then what we have shown the square of this is this one. So this means that what is z times w is plus or minus absolute value of z, absolute value of w, but it cannot be minus because absolute value is positive. So you see, algebra is much simpler if you do it in this way. This is more effective. And if you go to advanced courses, it is usually better to try to work with the set of complex numbers rather than changing it to the real part and an imaginary part and switch it back. If possible, it is better to do it in that way. But of course, to prove this in this way, I have to prove this one first. But to prove it in that way, I can just immediately start. Okay. So I think the lesson is very long now. It's not finished yet, but I think it would be a good idea if I stop here. But before that, I just want to write something for you. What happens if I have a complex number and raise it to power n and then take the absolute value? Do you think I can replace these operations, meaning that first I take absolute value and then raise it to power n? Do you think that these two are the same or not? Is it correct? Yeah, that's also correct always. So remember why. For example, let us consider it for natural numbers. Okay? So if I ask you what is z to power n absolute value, what is the meaning of z to power n if n is a natural number, means z times z times z how many times? N times. Yes? But now we just learned that if I have the absolute value of the product, it can be the absolute value of each one of them. So it can be written as absolute value of the first one, multiplied by the absolute value of the second one. But of course, if you want to be really rigorous, you have to prove that this will work for more than two. But that can be done easily using mathematical induction. Okay? And then what you have n factors again. This becomes absolute value to power n. But this proof is only for natural numbers. You can also prove it for negative integers. It's not hard. Because what happens if I have a negative integer? I can write it first as this. And then using that rule, I can write it as absolute value of the numerator divided by absolute value of the denominator. But absolute value of 1 is 1. Absolute value of this one is this one. Then I bring it up. It becomes negative. So this means that is also true. Yes? Okay, by the way, what you mentioned, Dennis, is completely correct. And that is called order. Lexicographical. So this should be like this. Yeah, that's called lexicographical order. So it means that that's completely this order. So it means that first you compare the real parts. Of course, you were considering right and up. I think the one that we consider is first we consider the real parts and then give the priority to up. But I think this will also work. So the lexicographical order is that a plus b, I, is smaller than c plus di, if and only if either a is less than c, then we don't care about what is happening for the imaginary parts, or a is equal to c and B is less than D. It's called lexicographical. It's like dictionary, yes. So first you look for the first letter, and then if the first letters are the same, you go and compare the position of the second letter. So this is called a lexicographical order. So if you want to compare which number is smaller than the other number, first you compare the real parts. If you know that the real part of this one is smaller than the real part of that one, you really don't care about the imaginary parts. So if the real part of this one is 1, and then we have 1000 I, and then this is smaller than -1 plus I. Why? Because when it comes to the real parts, 1 is less than -1, I don't care about the imaginary parts. But then, if that is the case, that they are the same, then I care about the second part. This is called lexicographical order, but of course we cannot just claim this is an order, but we have to convince ourselves that this really orders complex numbers. But this is the point. That is the sad news. We cannot keep the order and we cannot keep arithmetic simultaneously. And that's clear, because in real numbers, if I multiply I by any number, if I multiply a real number by itself, it turns out to be non-negative. Okay? But if I want to keep the order and I want to keep the arithmetic, then this should be non-negative, but that is strange because -1 is greater than 0 is not working. So it turns out that if you care about the order, you have to sacrifice somehow the arithmetic. And if you want to keep the arithmetic, you have to sacrifice the order. Okay? And this, what we want to do, we want to keep the arithmetic intact. So it means that there is no way for us to compare the numbers, yes, and keep the algebra the same. So this is why we do not have inequalities in complex numbers. For example, in real numbers, I can ask you to solve this inequality. But in complex numbers, I cannot ask you to solve this inequality. Yes? Because we are doing that part of complex numbers that we have sacrificed the order because of the algebra or arithmetic. Yes? So you shouldn't expect something like that in the complex numbers. Okay, but this lesson is not finished. I will continue the rest of it next time.
Okay.
Okay?
Thank you.
Thank you very much.